Hello, linear algebra student. This video is for chapter 1.4, part 2. We're going to talk about solving matrix equation AX equal to B and figure out without, even if we don't know what the B looks like, some information about the possible solutions of the system. Okay, so in part 1 of this video, I was working on this example and I say, we want to solve AX equal to U, and we say, okay, if to solve this is as if doing a reduced row echelon forms of the augmented matrix with A in the front and then U at the back at the right hand side. And I did not write down RREF, so the row echelon form, if you look at this, is of C. Oh, is it F? Yeah, F is what my matrix is 945, right? 945. So it is row echelon form of F. So when I do reduce row echelon form of F, I get 1 0 negative 1 0 1 2 0 0 0. That means there's solution, and the solution is x1 equal to negative 1 and x2 equal to 2. So based on the row echelon form, so that is, you can say U is in the plane. Spanned by that, and actually U is equal to what? One, is it 1 negative 2 or 2 1 2 what? Negative 1 2 negative 1 2. So U is negative 1 times the first one 1 negative 2 1, and also 2 times. So these two are the answer, right? Answer x1 equal to that. So this if you write it back is like x1 equal to negative 1, x2 is equal to 2. So and these are the weights of the columns. 2 5 1 negative 3. So it is in the span. So you can see to solve a matrix equation is actually solving linear combination. The next things we're going to talk about is theorem 4 in the textbook, and this is a very important theorem. We're going to look at investigate A. Now A is the coefficient matrix, so don't be confused by the augmented matrix. When we solve equation, the one that we input in decimal matrix decimal is an augmented matrix, right? Right. The rightmost column is the B column. But this theorem is about just A, those individual columns of column vectors. So what they're saying is, just imagine if AX equal to B has a solution for each B, then these are also the valid. So that means every B has a linear combination. That means the column A span Rn, and also A has a perfect position in every row. Now this is something that we never talks about. Usually we talks about perfect column, right? So what does it mean to have a perfect position in every row? So if you have, look at the example that we have earlier. If I look at this, we know that this is x1, this is x2. If and then this is the last one. So if I have, so this is the one of the variable, this is another variable, right? So if all of this, so x2, so if I have perfect column, perfect position here and perfect position here, it would cover in every row, then it would cover my my you know my variables, my unknowns. So if A has a perfect position in every single row, so this one, it doesn't count, right? This one is B. So in this case, I have exact solution. So if you look at, so this is a very important thing. If every A has a perfect position in every row, the row has a position in every row, say for like 1, 1, 1 for 3 by 3, then you can solve any B. You have answer for every B. Okay, remember this is A, not the augmented. Or if you have 1, 1, 0, 1. So you have more row, you have more columns, but then every row you do have a perfect position. This is already every row. Then you can solve for x1, x2, x4. You can solve for it. Okay, you can solve for it. So you can have a solution. So you would not have no solution. Okay, so let's look at this. A few examples. Example 1, use theorem 4 to show that this does not have a solution for all possible. So B, for B, so we are looking at AX equal to B, right? By default, this is what we are trying to solve, AX equal to B. And to check the possible solution, you only look at 4x, -2, -4. Just A, not the augmented, because you can put B1, B2 on the right-hand side. So, and then you do the row echelon form. Did I have it here? 4x, -2, -4. Oh, here, 4x, -2, -4. So I'm going to do D for this. Oops, sorry. Capital D. Yeah, D. And it become 1, -2, 0, 0, 0. -1/2, 0, 0, right? So this is the perfect position, but that's it, right? So I don't have, not every row has a perfect position. I can only solve x1 equal to something. X1, so like this is another, the B is over x1, x2 equal to something, but then x2 is free. And I really don't know if this is a B, this B, like if you just imagine the B column, this would be unknown, right? So this is unknown. So you cannot guarantee that it has solution for, what is that, prefix position. Oh, this looks really funny. So it does not necessarily mean does not have solution for all possible, for all B. Because a row of B is a canoverm, meaning on the right hand side, if this is actually an augmented matrix, I could have 0, 0, 1, which give me no solution, and I could have 0, 0, 0, which give me infinite solution. So it is not clear. But if I have perfect position in every row, then it rule out all those cases. So that's why you must have solution in all cases. Okay, so does not have solution. So describe the possible value of B where it has solution. So what is possible? What is the possible values of B then? Right, so the possible value of B would be, you have to do a manual row operation. So what you do, you start off with 4A of the augmented matrix, -4, and then you do B1, B2. So now you want to get rid of this 8 here. So what do you need to do? You do -2R1 plus R2, right? And put it into R2. So I have -8, 4 times -2, -2B1. I'm going to add 8, -4, B2. So I would have 4, -2B1. The second would be 0, 0, -2B1 plus B2, right? So when does it have a solution? It have a solution. Solution is if what? -2B1 plus B2 is 0, right? So this is the condition for it to have solution. If it's anything other than that, there will be no solution. Another example, the more complex one. So similar. So I have A and a B in an equation of ax equal to b, can I have solution? Can I have solution for all b1, b2, b3? So we just have to check just a, right? 1, -3, 5, -3, 2, -1, and -4, 6, -8. Does it have all perfect position in all four row? So we will do a row echelon form. Just the A, 1, -3, 5. I think, did I have it? 1, -3, 5, -3, 2, -1. Is it right? Yeah, it is correct. So it is -1, 3, 5, -4, 6. Okay, so it's E. Okay, so I do REF of E. It is 10, -10/7. So it's kind of funky. So let's write down. So 1, 0, -10/7. 0, 1, 6/7, and then 0, 0, 0 again. So again, only two row has the perfect position. So I might have solution if this is not a 0, 0, b. I would not have solution if this is 0, 0, 0. I might have zeros if this is 0, 0, 0. I might have solution, but it would be infinite solution. I might not if it is b 0, 0, 0, b, which is b is not 0, right? Or another number. So that's not at all possible. So we will say no. Um, ax equal to b does not have all possible solution. That means you cannot use it to generate anything you want. Because sometimes you would have no solution, sometimes you have many. So what would it take B1, B2, B3 to have a solution? So we'll have to do by hand. So let's see if I can have enough time to do it. Let me see. So I'll write it as 1, -3, 5, -3, 2, -1, -4, 6, -8. And I want to get rid of this 2, 0. So R1 times 3 plus R2, right? Put into R2. And that would become R1 times 2 would be 3, -9, -12. Oh, I have to B1, B2, B3, right? 3B1, I'm going to add to -3 to 6 B2. So you can see that is 1, -3, -4 B1, 0, -7, -6, 3 B1 plus B2. And then the last one would be, how do I get rid of that? It would be -5 of R1 plus R3. You will go into R3. So -5 of R1 will be -5, 15, -20. Oh, is it -20 or 20? Negative. Oh, it's +20. -3, -4. So because I changed multiply by negative. Yeah, this is 20 and then multiply by -5, no, -5b1, I add 5, -1, -8, and then a b3. So this becomes 0, 14, 0, 14, 12. Okay, -5b1 plus b3. -4 times -5 is 20. I think. Okay, so we need to get rid of this one now, right? So do we have enough time? I don't think I have enough time to finish this. So I am going to finish this in the next video. Okay, watch the next.